guys. So we are getting closer to the end. We're a little bit more than halfway through for the semester, and we're going to switch gears quite a bit. So we're going to move away from carbonyls as much and move on to two other areas of organic too. And before we wrap up at the end of the semester, which is going to be an introduction to biochemistry, structure, and function. So, kind of an introduction to what Dr. Shelby teaches, but not like a lot of details. So, if you're taking biochemistry with Dr. Shelby in the fall, this is going to give you just a quick little introduction, kind of what she does on the day one. So, what we'll do the entire week is what she probably does in an hour. So, we're going to do a couple of things in chapter 16. So, but there is several things in chapter 16 that is not going to be covered that I want to point out that you have just a basic kind of understanding of it, but not that you're going to be tested on it. And there are two things that are fairly simple that I want you to read on your own and look at your own. And I know several of you have told me you've never read the textbook. This is not the time to continue doing that. So read through it. There are two main sections that you're going to be responsible for on your own, and that's heats of hydrogenation as it pertains to dienes, and also UV vis spectroscopy. So if you've just been doing the diagnostic off the top of your head and wasting your time Googling everything, this is not the time to continue doing that. Read those sections, make sure you understand those sections because you're responsible for them. You're also responsible for naming alkenes, which you've already done in Organic 1, but we'll continue doing that in this semester. What we will cover in class is electrophilic additions when it comes to dienes or trienes, etc. You've already covered electrophilic additions, so we're not going to revisit that in any great detail. We're just going to look at what happens when you have multiple double bonds. And I briefly talked about it in Organic 1 if you had me, but we didn't spend a lot of time on it because it belongs here. The other part of electrophilic additions that we did not talk about is what's called pericyclic reactions, and it's basically reactions that the electrons are basically flowing sort of in a circle, and there is no polar component. So far we've only been focusing on polar reactions, meaning that you have something that's very clearly a nucleophile and very clearly electrophile reacting with each other. In our reactions, there is no clear nucleophile and electrophile unless you pay attention to how I'm going to explain things to you. Then you'll know what's the nucleophile and what's the electrophile on our reactions. But in the mechanism, there isn't even a clear indication of what that is. We're going to look at specifically of all the electrophilic addition reactions in under pericyclic reactions, the Diels-Alder reaction, which happens to be one of my absolute favorite reactions. One of the reasons why is it every atom that you use in the reaction ends up in the product. So the atom economy is 100%. And we can make such versatility in these products that we form because it's just based on what you start with and everything then comes together, and the stereochemistry and regiochemistry tends to be conserved in the reaction, so we can get all sorts of things, but you always form a cyclohexane ring, and that cyclohexane ring is the foundation of many natural products, and so we see that these compounds can be very useful. I do want to suggest that you also revisit spectroscopy. So when we talk about conjugation, and this is one of your things that you need to look at in terms of that UV vis that I'm talking about. This is part of your own reading. We're going to do some problems related to it in class, but it is something that is on your own. When I talk about conjugation, we're talking about double bonds altering. So you read about that in the textbook, and if you didn't read the textbook, please go at least skim the textbook. And so lycopene is a compound that has lots of conjugation, and isoprene is a compound that does not have very much. So it has a little bit. And isoprene is colorless, whereas lycopene, is in things like tomatoes and watermelons. It's actually what gives it the red color. And because if you remember in from high school or middle school or whatever, we know our little color wheel. If something reflects the color red, it absorbs in a color region opposite to it. So for lycopene, it actually absorbs, its lambda max is around 470, which is in the blue-green region. And on the other hand, isoprene doesn't show up in the visible spectrum. It only absorbs light in the UV region. And there is a correlation between the energy it takes or the wavelength you have. There's a relationship in Gen Chem that you learned about energy and its relationship to, I'm not going to put in proportional, but there's a relationship to wavelength. And remember, wavelength, the symbol is lambda. And so the highest energy associated with that, there is a relationship. Now, it's not 100% perfect, but there is a relationship between that energy and that wavelength, therefore, and color to the energy associated between the energy gap associated between the HOMO and the LUMO of a molecule and the HOMO and LUMO energy values. There is a correlation between how big that energy gap is and conjugation. So I want you to kind of look up what is the relationship between conjugation and the HOMO LUMO value. How does the energy gap associated with the HOMO LUMO, how does that relate to wavelength? And so we know from Gen Chem there's a relationship between energy and wavelength. So revisit from Gen Chem what that is. Then look at how that energy then relates to the wavelength and how the energy gap comes from the HOMO LUMO. So look at that. And so our chapter question, and this version of the textbook, it's chapter 16. My chapter question is explaining why isoprene is colorless and why lycopene is red, meaning that it absorbs in the blue-green region as it pertains to the HOMO-LUMO gap. All right, so let's talk about what conjugated versus other kinds of dienes are. So conjugated just means that we have alternating double bonds. We're still sp2 all through, but there is a single bond in between. So even though those carbons are sp2 hybridized, it's a single bond in between. The cumulated double bond, and another name for this, and you should know this name, is called allenes. And so this is actually something that I studied when I was in graduate school, how to make these. These are actually really difficult to make. But you basically have sp2 carbons on the outside, but this middle carbon, it has two sets of double bonds, so it's actually sp hybridized. And because we can't put those p orbitals on top of each other, they're orthogonal to each other, so they're kind of perpendicular to each other, which creates kind of a little bit of repulsion. So the double bond on one side, like we see here, they're going to be kind of on the same side, but the double bond on the other side is not. And so even though they're kind of at an angle to each other, it's still not terribly stable, so they're hard to make. And we've seen isolated double bonds before. It just means that they're not, there's no single bond in between. So I do have a question for you based on this. Can you identify whether this is conjugated, cumulated, or isolated based on what we've said? All right, so we are focused on this chapter on multiple double bonds, but specifically conjugated double bonds. They have some very interesting properties. And if you draw the resonance structures, you can see you can delocalize all your p orbitals with each other when they're conjugated. And so that's what makes your molecule relatively stable. So the more conjugation you can have, the more stable you have. But also you learned in Organic 1 about our pi bonds and the how much substitution you have. So think back about stability of pi bonds and the substitution that you have, and then also now throw in conjugation. So the more conjugation you have, the more stable something is, but then think about substitution and answer this question. All right, so conjugation is not just for carbon-carbon double bonds, but we can have conjugation with heteroatoms. Heteroatoms meaning other atoms other than carbon and hydrogen. And so we've seen this actually before when we talked about alpha beta unsaturated carbonyls, and the reason that they formed from aldol condensations is because they're so stable. They're even more stable than normal carbon-carbon conjugations. And so we see these types of things. We also learned about where on these molecules things attack. So for instance, we talked about on Michael additions, we actually do our reaction where they happen at the, and I didn't draw this in the right places. I was just speaking. But we learned about on Michael additions, we attack at the beta position, and that is, basically 4 positions is, away from where the second thing happens. So we'll talk about that again in a second. Versus just attacking at the carbonyl. There's some aspects of what we're going to talk about here that applies to that as well. We can also draw resonance structures, and I would suggest that you pause here. This is a good place to pause and try to draw these resonance structures, try to practice these resonance structures. But this is actually something that will help you understand why we have so much stabilization. There is so many different kinds of resonances that are associated with this. So we can essentially draw all the arrows, and I'm going to do one for you, but I want you to practice on your own the other one. So to go to this resonance structure, I can move my arrows this way. Okay, so try to practice this. Try to feel comfortable with the fact that one of the reasons for the stabilization is the delocalization of those p orbitals. Now, one of the things that is going to be prominent in this unit is going back to talking a lot more about molecular orbitals, not just HOMO and LUMO energies, but also the shapes of them and what kinds of things that can happen. So when we have these conjugated double bonds, they can be in 2 different orientations. So we've learned about the term cis and trans. This is a new term, but S-cis and S-trans is similar. The cis means that you have the same group across a single bond. That's what the S stands for. Across that single or that sigma bond, the double bonds are on the same side. So the definition of S-cis means that across the sigma bond, the groups, that does not look like sigma, across the sigma bond, the alkenes or the double bonds, whatever the double bonds are on the same side. Okay, so it's a little bit different than when we talk about cis and trans normally, and trans is the same way. Now, kind of obvious, but the cis is not very stable, and we can think of it, you have these p orbitals and they're closer to each other. So if my thumbs are your single bond, and my other fingers are your pi p orbitals, they're on the same side, and they're going to cause some repulsion from those electrons, whereas on the trans, they're on opposite sides of each other. But this is going to pose a problem for us when we do certain kinds of reactions when they're on opposite sides, even though that's more stable. But depending on the energy of the system, so depending on what the energy is, if I increase the temperature, I can allow for that rotation a little bit easily. Now, it is a difficult rotation because you're talking about rotating around sp2 carbons, which is not very easy to do. It's not just purely, even though it's a sigma bond, it's not sp2 carbon, so it's not easy to rotate. And we'll talk about that also from the perspective of the molecular orbitals. So just to review molecular orbitals, and there are some handouts about HOMO and LUMO that I posted early in the semester in Organic 1, but your molecular orbitals are basically what forms when your atomic orbitals or your hybrid orbitals are going to overlap. At a certain point, there's so many of them that it's just a lot going on. So for us, we are going to only focus on the p orbitals. That's because we're focusing solely on pi bonds, so we're going to only focus on the p orbitals for the purpose of this unit. There are other molecular orbitals that exist, but we are going to focus only on the p orbitals. That will simplify what we're talking about. So if you're in inorganic chemistry or physical chemistry or whatever, you'll probably talk about all of them. We're going to focus only on the p orbitals to simplify this concept. But when we think about molecular orbitals, one thing that we don't really always talk about, but it's something you learned in Organic 1, is that you're basically bonding the atomic orbitals across the molecule. And we see this especially when we're talking about ethene. So this is ethene and it's double bond. When the electrons from one p orbital of one carbon and the other p orbital come together to form your pi bond. So again, I'm ignoring all the other molecular orbitals. You're spreading that electron density throughout the molecule. Now, it's a different story for the LUMO versus the HOMO. The LUMO has nodes in it, and we'll start talking about what kinds of things that's going to do. But what it does is by spreading the electron cloud through the molecule, we're adding stability, okay? So we're adding stability onto your molecule. And so to revisit from Gen Chem, what is a node? A node is a place that lacks electron density, okay? So